Good morning and welcome to today's debate. It's making ovens smarter. Reflow ovens have become more sophisticated and dynamic in recent years. They're looking at things like low voiding and opportunities to reduce energy and of course extracting data for the new smart factories of the future. I've got an expert panel here this morning to discuss this, and going from right to left at the far end, we have from SMT Wertheim in Germany, we have Maximilian Leppig. To his left we have Fred Dimock from BTU, and to my immediate right we have Michael Hanke from Rehm Thermal Systems. Welcome, gentlemen.
Good morning.
Thank you.
Good morning.
So we're going to get started. I have a feeling we're going to have a robust debate this morning. You all seem to be in good form. So let's get straight in with the first question, which is, what is the most effective and cost-effective method for reducing voids in reflow systems? There's a number of methods in the market, ranging from control of fluxes to vacuum systems to the
vibration
systems. Mm-hmm. Well, not really vibration. No, they're the ultrasonic.
Okay.
So let's start with you over on the end there, Maximilian. What's your view on this?
So we as SMT, we offer the high quality solution. We do the vacuum system where you can achieve like up to less than 1% of voids with that solution. Mm-hmm. And one good point about that thing too is that we can usually use the oven with the normal reflow profile as well. So you don't need to run it always with the vacuum. You can run it with the normal reflow if you have products that don't need that voids, that void ratios, right?
Right.
So that's
so you don't need to run it under vacuum. I thought you had a vacuum system in the center of your machine where you.
So the vacuum module is actually right after the peak zone and before the cooling zone. So you can just turn that on or off. If it's turned off, the chamber will stay open and the product will just pass it.
I see.
And you can just run it with normal reflow.
I see.
As
Which
well.
is good if you're doing high mix, for example, and you've got some boards that are not requiring that.
So you have different opportunities and you don't only need to run it with vacuum.
Okay. Fred, you.
Yeah, I think there are two parts to your question. The first is, what works, right?
Yep.
And the other part is what's cost effective.
Correct.
Okay. And I think that a lot of people have shown us that vacuum reflow works very well. Yep. I don't think there's any question about us getting low, down low in the level of voids. What I'm seeing going on is a lot of people, paste manufacturers, are working on pastes that are lowering the levels of voids. We recently did a study using a standard paste where we ended up with like 34%. This is on QFNs. We ended up with about 34% voids on a standard paste. Then what we did is switch to a low voiding paste and ended up with about 15%.
Right.
Okay, just by changing the paste.
Yeah.
But that was 2 generations previous to where we are now in the paste. I'm hearing people today talk about just from changing the fluxes, getting down to 5%. I've heard a couple people talk about 2%. Right. So I think that when we look at voiding, we have these very good equipment-oriented fixes, but we also are headed very, very strongly towards some paste changes, fixes.
Right. Yeah.
And I put this in the same realm that happened to us when we went from tin lead solder to leaded solder.
Right.
When we started that originally, we said that, if you're going to use the SAC materials, you have to do it in nitrogen. That was the first one, and it wasn't going to look as good as tin lead. Right. Today, we're absolutely able to do SAC 305 in air without any of the problems. They look very, very good. So I think that there are going to be people that say, yep, I absolutely have to have vacuum reflow. But I think the most of the industry will ultimately get to the area where they're using the newer solder paste.
I think the consensus I've had from people I talk to about the subject regularly is that the optimum thing is to use a combination of both. to use a paste that's got one of these low voiding fluxes and use either vacuum or the frequency system to get down below the 10% and get down into the sort of 1 to 2% range.
I've also talked to a couple of the paste guys, some of the R&D guys, and they think that not necessarily the full piezo vibration is the answer, but some type of movement to break the surface tension will allow the voids, the gases to come out.
Yeah, but when you're in a reflow oven,
that's a tough
creating movement is always
right.
fraught with danger.
That's going the wrong way.
Yeah, Michael, what's your view on this?
Yes, Rehm is a partner also in process technology. I think this is very important that we discuss it with our customers in advance to help also to understand their process. I think this is the beginning, and then when we understand and also the customer understand the process, then we have different tools also to reduce the voids. Right. That's not only the paste, that's not only all the material that we use. This is, for example, for sure also vacuum. We as a reflow supplier, we supply also our system with vacuum. Vacuum is very common nowadays, and we have experience longer than 20 years also with vacuum. But it's not the only solution, for sure. Right. I think this is a mixture to understand better the process. Yeah, optimize the profile, optimize the paste, and at least to have a stable, continuous process is achieved with vacuum. Yeah, these are the results also to reduce dramatically the voiding with our vacuum solutions. Yeah. And important is also in case of the throughput and the cost that we can also offer this in a dual application. Yeah, so that means also we have higher throughput. And this compensates also the costs. Right. This is very important.
Absolutely. Okay, good. So let's move on to our next question. Efficiency in reflow is incredibly important. What steps can manufacturers take to reduce consumption of electricity and nitrogen to their systems? Let's start with you. We'll start it the other way around.
We as Rehm, we optimized our insulation. Insulation, in this case, that we use also newer material, innovative material, also to optimize the isolation itself. The insulation, this is one of the basics. Yeah? Okay. To have also a lowest energy cost. This is one of the base, like you build a house. Second is also we optimized also our motors that we install in our equipment. These are energy safe motors. Nowadays also with intelligent digital information that we can use also later on to optimize profiles, to optimize the maintenance and all this stuff. Regarding the nitrogen, we have optimized nitrogen regulation. Important is also that you know immediately what is in the process, what happened in the process, which nitrogen you have really in your process. This is to guarantee for the process quality at the end. And therefore, we need a really fast nitrogen regulation, and this gives the benefit that you can shrink dramatically also nitrogen in our systems.
Right, so you reduce the amount of nitrogen you use by more careful management of it, more careful management of the profile, and then of course insulation. That's really your combination.
Yes.
Fred, you have a system that looks at the downtime, or it doesn't take the electricity down to zero. It doesn't switch the machine off when it's going idle. It takes it down to a sort of idling speed, as you like, and then it has less to climb back up. Is that your? That's
correct. We have a system called Energy Pro, and what it actually does is when there's nothing in the oven, and this is fully settable by the user, but when there's nothing in the oven, what we do is lower the belt speed to about a half inch, to the lowest it'll go. And at the same time, what we'll do is lower the static pressure in the oven. Okay, in our ovens, what we do is we actually control the fan speed, control the pressure within the plenum by controlling the fan speed. Okay, so we'll lower that down to the minimum. And we do that when there's nothing in the oven. And it automatically will switch to that. And what it does is saves about 25% of the energy during the downtime.
Yeah.
The beauty of that is that if you put a board and present it to the oven, hits the sensor at the front of the oven, the belt speed automatically increases very quickly, the static pressure comes back, so the board sees absolutely no difference in the thermal profile. So during downtime periods, even if it's a short time, right, what we do is save 25% of the energy.
Right.
That's what we call a standby mode. We have another mode that you can set that goes to called a sleep mode. And in that case, what we do is take the higher temperature zones and lower them. Let's say we bring them to 150 degrees C.
Right.
Okay? We add that into the sleep, and what that does is lowers the energy of the oven by about 40%.
Right.
It's a big savings.
Wow.
Now, somebody will say, well, gee, it takes a little bit longer for it to heat back up, and that's true. But then we have the ability to move a sensor further down line. So if you put something like just before the pick and place machine, it gives enough time for the oven to get back up to temperature.
Yeah.
During these times, if it's a nitrogen oven, what we do is we lower the nitrogen flow so that we don't have to bring the nitrogen back in to be able to purge the oven back out.
Right.
There's a third step, which is called hibernate. Okay? In a hibernate, we basically shut the oven off.
Yeah, basically.
Except we leave a small amount of nitrogen flowing.
But you know, it's a very important topic, you know, because we're all living in an industry now where we're driving towards smart factory.
Yeah.
And one of the big areas that smart factory is going to make a big difference once it starts kicking in and getting really optimized is in machine downtime.
Right.
So you know, we're not going to have the luxury of these long ramp up times, you know, for ovens to get back up to peak temperature. So having more tighter control of the energy and the heat is going to be more critical going forward.
Correct. A parallel part of this system is to be able to log downtime, time where the oven's ready to go but waiting for product, right, when the oven is going through its heat up cycle, and be able to get all of that data. We also have the ability to add into that the cost of nitrogen into nitrogen flow, the cost of electricity, and monitor the electricity cost, and bring that up on the screen so that the customer can go and look at that and say, you know, this is an area where I'm losing some money. I can make a change to make that work. And what that does, that really relates back to that factory system, you know, where we're saying, where can we start saving money? That to me, that's a phenomenal area for
you know, reducing downtime is going to be a big potential for saving money too.
That's correct. You know, you go a step further with that. One of the machines we have at this show is a dual lane, dual chamber machine. But that was driven by a customer that said they wanted zero downtime at the reflow oven. Okay, so the machine has the ability to have one lane running lead free and the other one running tin lead, right, and just switch the board over to the other lane. But what we found with that, we could actually shut one lane off completely, and the other lane was absolutely perfect. It had profiles that were very repeatable.
You could be doing setup for the next job if somebody's doing a high mix environment or something like that.
That's right. So they could just switch back and forth very quickly.
Interesting. Maximilian, you've got a system where you're using these lambda sensors to independently control each of the fans, which gives you a lot of flexibility. So what's your approach to the energy?
We do have different approaches on the energy type. So first of all, you're talking about the lambda probe. We have a lambda probe right in the peak zone. You can measure the ppm level of the nitrogen in real time, and we have proportional valves where you can really adjust the nitrogen consumption. So you have a straight line of the consumption, not if you're talking about a bypass control and always have this on-off valves that only shut down and go up, and you'll have this real peaks in the consumption as well. And if you use our intelligent control, you'll save up to 20% of nitrogen.
Really? Okay.
Yeah. And talking about electricity as well, we use frequency inverters with always a stepless control. So if you look at the consumption of a fan, you'll have like a curve that really rises up at the end. And normally you can use your profiles running at we have this 1 to 4 stages. If you run a profile with stage 4, you can probably run it with stage 3.5 as well, and you'll save 20% on the blowers. And the fans are 50% of the whole energy in consumption. And another thing is you set the temperature at like 10 degrees higher or something like that, because the heating elements are not always turned on. So you'll save in the frequency inverters, in the fans, energy again. And so we're doing different approaches there. One other thing is our cleaning system. So in the hot environment, we're cleaning with the ABS. So it's a pyrolysis cleaning. You'll have a heating element, and that breaks down the flux because of the heat, and the granulate will get the flux out there. And then you get the heated process gas back in there. So you don't cool anything down and need to heat it up again and get energy in there.
That's
for
a closed
that.
loop process.
You have the closed loop. You don't lose energy because of that. So really focused on energy consumption and nitrogen consumption as well.
Wow, it's interesting to see how you all have very innovative approaches to this issue. So looking ahead at our next question, how do you define what is the optimum length for an oven? It's a fairly basic question, but I'm thinking here of somebody who's maybe got a high mix environment.
I think the length of the oven, one is very important. The oven should not be the bottleneck in the complete line. So we need to discuss also with our customers what is the real request, what is the throughput, and therefore we have a calculation tool. That means also then it's optimized the length, if it is also a single lane or a dual lane or up to a quad lane. So we had also the possibility to run in a small length, a high volume and with a high mix. And this is one of the facts that we are so flexible. Not only the length, so we can use also the width with more lines for in the transport system.
Okay, makes sense. Fred, I think if you're talking to an OEM customer, it's a fairly easy decision, because they're making the same thing all the time. But if you're talking to someone who's doing a lot of high mix and doesn't know what they're going to be making in 6 months' time, how would you advise them?
My advice generally to people, especially the high mix people, are to go with a medium length oven, and in our case it would be either a 100 or 125 inches of heat. That's an 8 or a 10 zone oven. Mainly because if he's got a real small running product, something with a small number in there, he isn't concerned a lot about throughput, but he needs the flexibility in the oven. If he's got a really high runner and he needs to have a few more items going through the oven, then those gives them the opportunity to at least run those levels. I do teach a class. It's a basic reflow class at SMTAI, and one of the sections that we cover is throughput. What size oven do I need? Right, and the whole game on that is time for the reflow part. Okay, so if you've got a longer oven, you can go faster and put more throughput. If you've got a shorter oven, you go slower, right? But it's always the same time within that heated section, and that's really the thing that you focus on when you're doing this. And so you look at your profile, and you can look at the profile that's needed, the requirements that are given by the solder base people, and say, this is the general time I need to be in there, and you can come pretty close on what you can on choosing the reflow oven that's best for your situation. But the high mix guys, that's where you say, gee, you got to kind of look at the average of what you're doing and do well on one end and kind of maybe hurt yourself on the other. Because you don't want to buy a big oven and have to run that, and then they're spending a lot of downtime. I mean, the real thing is to stay with the medium-sized ovens.
No, you could buy a Ferrari and just run it at very basic speed. It'll last forever.
I don't know if you ever tried to drive a Corvette in the snow, but that's not a lot of fun.
Okay, Max, what's your view on this?
Yeah, totally. I mean, if you have a high mix on products, you always need to have like a buffer to have for the future as well. But what we see as well is if you have like an AOI system or something around that after the oven, and you'll need like 50 degrees Celsius, something like that, out of the oven, we are pretty flexible in cooling zones as well. So at our machines you can choose between 2 to 5 cooling zones. You can have it with air, you can have it with heating exchangers, and you can have it with internal cooling aggregate, external cooling aggregate. So really flexible in terms of cooling as well, if there's needs in that.
Excellent. Okay, moving on to our next question here. What, as I mentioned earlier today, we're talking about smart factory. It's pretty much been the theme throughout the week here. Smart factory is demanding a lot of data coming out of every piece of equipment on the production line. What can we currently extract from the Reflow system?
What we currently can extract is all the process parameters, all the relevant parameters, what is needed also for the quality. This is not only the profile, this is not only the nitrogen consumption. This is also about the energy. This is also the functionality if the board runs very well. So we have optimized software, capability test software that runs all the time and checks if all PCBs run very well and gives also a green light. So we have also that in our systems installed already. So the customer is sure all the time runs in the best quality that we can achieve.
Right. So basically, but can you extract a lot of the data off for further analysis? I mean,
yes, we can extract it. We have a Microsoft XML interface that we can use everywhere. So we can use it on an MES system, we can use it on an ATAC system, and all our systems are common in the world. Our software, this is I think very, very important, runs on the Windows, so we have all possibility. That's a really open software where you can configure on the easiest way that fits for the customer need. So we can customize the interface all the time in a simple way to satisfy the requirements of the customer.
What sort of data are you bringing off of there? You obviously the temperature profiles in each zone.
The temperature on each zone, nitrogen, also timestamps is very important. Also consumption, what will be the real costs for this board in the Reflow system. This is also possible with our system. So we have also a calculation tool integrated, and this helps. This helps the quality manager, but it helps also the manager and the purchasing guy who count also how much nitrogen expend. Yes.
Okay.
Yeah, I think
are you getting asked? Are customers asking you guys for data? Because I mean, at the moment, a lot of the smart factory stuff stops before the Reflow. It's all done upstream, but it's increasingly going to come downstream. I mean, in my view, it's eventually going to encompass everything on the line, and it's going to go then down to the materials level, which will then come back full circle to what happens within the Reflow. So, are you currently getting asked for data from customers at the moment?
Absolutely. We, like most other people, have a very large amount of data available off the oven. It's real, lifetime, and it goes into files within our control system. And people come to us and they say, they want to use that in their factory system, right? And what we do is we partner with them to find ways to get our information to them, to their factory system. The problem we run into is that you can talk to 5 different people and they got 5 different systems. Right, and that's the real issue. That's the real issue that goes on today. I understand there's a subcommittee for IPC that's trying to deal with this, come up with a standard, so that we're not reinventing the system every time we do it. And that IPC committee has an awful lot of disagreement going on within it. And it's hurting us.
It's hurting everybody. And in fact, I was discussing this with Phil Stoughton this morning, and we both agree that IPC's got a 6-month window here, maybe to the end of the year, to deliver something on this, because otherwise people are going to go in other directions.
That's right. Right. I would say that I know of at least 4 different groups of people that we're working with, large companies, that are asking for things, and we're doing customized solutions for them because we have to. And we're even down to the point where we don't know which language we're using to transfer data. I mean, you talk about HTML, but there are 2 or 3 others, and people are going completely different directions. The information is there. We've got it. I think we all have it. The only problem is how do we get that into the real factory system?
Right. Well, I mean, this is the thing. I mean, actually taking the data off the line is relatively simple. It's getting the engine to translate that data into actionable instructions. That's where the bottleneck is, but it needs standardization to really make it work and give everybody a platform to work on.
That's right. We do it. Part of that comes like our Energy Pro, like I mentioned before, where we know what the downtime is, we know what the waiting time is, we know when we're going through the transition from one recipe to another. On top of that, we data log all of our recipes, right? Every recipe that we put in has a change log that goes with it. So if somebody goes in and changes it, and you get these in the manufacturing facility, right? So somebody changed the recipe, right? Well, we got the ability to go back and say, no, we know when they changed it, and this is the person that was logged on.
You got fingerprint detection on it.
This is a little bit more than traceability.
You need that guy on the third shift to leave things alone.
But I think you can collect a lot of data. Important is what is the important data that they will use also to improve their process, improve also their quality, and reduce the cost. This is very important. To collect all the data, big database. This is one of the facts that we have here. We have a storage. Everything is possible, but important is also to help the customers. What is very relevant for their process.
Yeah, but I mean, I said this also earlier this week. Was I was in Japan a couple of weeks ago. And, Cisco presentation, and they were saying collect everything because you don't know what you're going to need in 3 years' time, and you might wish you'd collect that data, but if you don't collect it, then it's too late.
Yeah, we collect all data. This is true, and I think this is a mass, really a big mass of information. But you should help also the customer to typically identify which data is relevant at the moment. For the future, you are prepared because you have everything. That is true. And our systems nowadays delivered hundreds, thousands of information every second, and we collect it and transfer it to their system. Right. This is already done.
The key in some of this is being able to even look at trends in the data.
Absolutely.
If you're looking at, for example, if you look at zone power, the heat of power to a zone, that's going to be consistent. But if it starts to change, it may indicate that there's something going wrong, and you need to go and look at it. Today, we've got the data, but we're not looking at the trends.
Right. I agree. Max, sorry to keep you on the end.
It's all good.
What is your view on this? I mean,
we're talking about this right now. We're getting tons of data. We're getting the temperatures, the nitrogen levels. We're getting everything out of the machine. It's not a problem, and it's always about standardizing, about getting the right information, about getting the trends right. So,
are you using your data for maintenance as well, for example?
Yeah.
Because
we do have some kind of predictive maintenance features. So, actually, through our frequency inverters, we're controlling the consumption of our fans and everything, and you'll get a message on the screen in the front of the machine if like the fan 4 on zone 2 is not running well, and you should better check it. So we're really good at this, or we're working on this stuff right now.
Okay. All right, so that sort of takes me into my next question, which is can these data be used to refine profiles in real time? What's your view on that?
I think that the answer is yes and no. How's that? Okay. When you're converting data from the oven itself into profiles, you need to do the work up front to the engineering work to be able to get the set points you need to get the profile.
Right. But
currently we've got a little bit of a difference in what goes on with the set point and the profile. Okay, and in that case, what we do is we look at secondary monitoring of the temperatures in the zones to be able to verify that the actual output has not changed. Some people call it virtual profiling. If you set it there and you watch how you're changing in the temperature in that zone, and you're making sure that there's correlation between the result at a level and the oven set point.
Right.
Okay, that's the way I see that being done, and there are a number of people that do that.
I think there's going to be a demand from the industry going forward, because it's part of the old Industry 4.0 smart factory thing again, because we're currently getting printers correcting themselves in real time and pick and place machines. The oven can't be the bottleneck in here. We don't want people don't want to be reporting at production meetings how much scrap we produced last week.
Yeah, right.
They want to get it up that information in real time.
Yes. Yeah, and then you start looking. If you start doing those sorts of things, then you start looking at the accuracy of sensors, repeatability of sensors. The long-term stability. And we're still learning, I think, some things about those.
Right.
Just look at just the thermocouple itself. It's amazing the number of times that I'll talk to people and I'll say, "Do you know how accurate a thermocouple is?" And they sit back and say, "Well, yeah, it reads the temperature." Well, guess what? These thermocouples, it's plus or minus 1 degree on these Type K thermocouples at these temperatures. And somebody comes and says, "Well, I want it to be exact." Well, guess what? If you got that is an issue of just the accuracy of a thermocouple. That doesn't even count about repeatability.
That seems a difficult thing because how do you make them more accurate? And are the finer thermocouples more accurate than the bigger ones?
I don't see that. They're more responsive.
They're more responsive, but then are they more fragile?
Yes. That's one of the parts of the issues. You like to have this nice, big, robust thermocouple in there, right? But they're not very responsive because they add mass to the item. When I was working at General Electric, working with some of the research guys, we were talking about how you do measurements. Okay, and one of the guys said, as soon as you put something in an environment to measure it, you've upset the environment. So measurements get to be kind of interesting. I think, though, from a general viewpoint, we on the SMT side do a very, very good job in measuring temperatures, in measuring what we need in our process. People once in a while talk about going to optical measurements, for example, and you start saying, gee, there are a lot of problems when you go to optical measurements. That works at some of the higher temperatures, things where you can't get into the environment easily. But I think what we're using now with thermocouples, RTDs, those types of things, those work fairly well. And they're very good for the environment we're in. We don't need to have absolute precision. We need to get close.
So what's your view, Michael? Is it a realistic goal?
It is a realistic goal. We from Rehm did it in this way that we use also our software, our ProCap software. This is capability software. And this gives the feedback on time, live, what is going on with the profile, and identifies if their profile is out of the range of this identical board, and then the operator gets the feedback very soon, and he can react if there is an issue there or that. And I think this is very important to create more intelligent systems where we have already had, in case instead to discuss all the time about the thermocouples, if the accuracy is the right or not. I think important is that our partners need a tool, instrument, to help them to identify in advance if the profile will fit to their requirements, and we have the solution now with our ProCap software.
Right. Max, you've got independent control of your fans. Are you able to sort of track trending in your systems and make alterations?
Yeah, so we actually do monitor the consumption of the fans. So we do see if a fan gets stuck or something like that, what should not happen, but at some point, if it does, you'll have a change in your profile, right? So we do monitor all of that stuff. And again, with the lambda measurement, we do higher the reproducibility of that profile as well. So we have a real stable consumption, and the consumption or the ppm level is always the same, so it doesn't change. So we do lots of things in terms of reproducibility and in terms of making all of that.
Okay. Right, so let's go to our next question, and that is, would a better understanding of material science and potential CTE mismatches improve profile capability? Who wants to pick that?
Let's start again.
I can see the look on your face. Don't ask me.
So I think important is, and this is realistic. This is life. Also to identify deeply which kind of paste you use. For example, and we have a big database for that the customer can use. Our profile creator, and this creator helps also to create the profile with the figures from the paste. So we have a big database from all of the paste we use in the market. Also, you must have the information which weight and the length and the size of this board, and then you get also this optimized profile in advance. And this is a tool that also reduces dramatically the cost and also the timing to create a new profile and optimize the profile.
Right.
And for sure, coming back to your question, it is related to the material, mostly related also to the paste. But these figures we have in hand now from the suppliers, and then we can also adjust the system in advance.
Yeah, you must gather a lot of data on certain sorters and how they perform when they go through your oven. So you must have a reasonable idea ahead of even running the profile of how it's going to behave. Right?
Yeah. Normally when I talk about profiles, what I do is go to the solder paste manufacturer specification. He's the person that knows the best about how his material works. If there's difference in thermal expansion between components, the key is to keep the differential in temperature as low as possible. We have an advantage when we're working with metals, because metals has the ability to creep and to move. They're malleable. They'll move and they'll relieve stress when it gets to a particular level. Now, I grew up in the glass industry and ceramics industry, okay? And in that industry, boy, if you didn't match the thermal expansion of things, or if you had things that locked together at a particular temperature and they had different thermal expansions, they could cause you big problems. Okay, and it wasn't only the difference from where they locked together to room temperature, it was the difference in how they came down in temperature, because some things weren't linear, and that they'd end up with gigantic stresses before they got to room temperature. Okay, but in the metal side, I think we're a little bit better off. The things that we have biggest problems with, I believe, is in cooling. Once we've locked things together on big BGAs, right, where we'll see big, heavy levels of stress, we'll see ball stripping, and a lot of times we can control that with very slow cooling. You know, we see some people on reflow ovens to get slow cooling, they'll move the peak zone back from the end of the oven. Okay, we have static pressure control in the cooler, so we can slow the fan speeds down in the cooler to make it go slowly. We've even had people come to us and want to add heat to the 50 degrees or so, where you add a little bit of heat to it so that you can slow that cooling down. The problem with when you start slowing the cooling down is it becomes out the end of the oven too hot. And well, not so much molten, but the AOI equipment at the end can't handle it. So I could see some people in there with a very large buffer that have outside cooling. Now, we do a very, very good job in cooling, and then sometimes in the BGAs, those big ones, we do too good of a job.
Why do they want to add heat to after the peak reflow on the cooling stage? Is it they want to have a slower,
very slow cooling?
Very slow cooling.
Again, go back to the SAC days. Okay, the original SAC days. The first, what was happening during those days is that I had people coming to me that wanted to have, less than 1 degree C a second in cooling because of BGAs, because they're worried about them stripping. We had other people that wanted very, very high cooling rates because they wanted to set up small grain structure to have stronger. They wanted to have stronger joints. And at the same point in time, we were getting the same questions from people going in different directions with almost the same type of material on their boards. Okay, so again, I think as we get involved in this, we get deeper, we'll get better understanding. But matching CTE or getting that as part of the profile is important. That's part of what the profile's about, especially during the heating and cooling.
Yeah, absolutely. It's such a major problem with electronics. I mean, if we could make electronics at room temperature, it would be fine.
No, wait, no, we don't want to do that. We need reflow ovens.
Nice. What is your view on having greater knowledge of material sets and CTE mismatches and that type of thing?
Yeah, it's totally about the mixture of the PCB, the solder paste, the products. They all have the specifications, right? And you have to find the real profile for that one in the end. Right. And you can adjust it with the frequency inverters, you can adjust it with the cooling, as you said, that you don't have the highest cooling slope in the beginning. And yeah, there's lots of values that you need to have a look at, and you need to adjust when you're setting up profiles for that.
Right, absolutely. Okay. Well, we're going to move on to our last question. We're starting to run out of a little bit of time. What, in your opinion, is going to be the next big development or significant development in reflow oven technology? Is it going to be faster profile changes, probably? Possibly? Michael?
Yeah. Thank you. No, the important thing is that we have a system in the future that tells the customer what to do. An intelligent system related to the Industrial 4.0, and this is the future. This is the future of the reflow technology, not only profiling, not only lowest maintenance cost, compared with this information sent actively from the oven, and this will be our next future to help also the customer, also to reduce all these costs and be more efficient without having all the information as we discussed at the moment, that we need this information. Hey, it's too much information. We have now our intelligent system. This gives you the information, this gives the customer the information, what to do, when is the maintenance, when to change a board, when to change a temperature, and this is linked with our partners in the line. This is very important, because we are not the one and only in the line. We will be, but we are not the one and only. And this is one of the parts that we have nowadays, also instruments, that they are directly linked also to the process before and also after.
Yes.
Important is also the inspection, the AOI, and so on. And this, we collect this data and inform our operators nowadays on their smartphone or on their iPads. Right. So we have these different solutions now, and the future will for sure, a proactive system gives all the time the information to the customer without touching the screen, without going to the machine. Yeah. An intelligent system, I think this is the case.
I think you're right. I think it's very important. I mean, we need all sorts of data off of the systems, most of which is already there. But what we do need is a way of translating that intelligently and making it easy for the customer to understand. Yes. If I can use an analogy, 20 years ago with your smartphone, you could do a lot of things with your phone, but it was fairly complicated to do it. You had to go through all sorts of menus and everything else. Nowadays, everything's icon driven, and you can do things very quickly on the phone. And we need to have that level of easy and fast.
Keep it simple for the operators. This is the idea behind, and that will be the future, definitely.
Yeah, I think so. Fred?
Yeah, I agree completely that we're getting closer and closer to the point where these machines are going to run themselves. Okay, there are two directions here. I go back. I drive. My one of my toys is a Model T Ford. Okay. Say Model T Ford. That's okay. Model T Ford. When I drive that Model T down the road, I have to adjust the timing as I'm moving with an arm. I have to reach over on the dashboard and adjust the carburetor by hand. Okay. When I get in my Chevy pickup truck today, I put the key in the ignition, I start it, and I drive. I don't have to adjust anything because the truck does it by itself. It measures what's going on, what it needs in timing. It measures what it needs to have for the fuel injections. Okay, that's kind of the direction that we're headed for
agree.
in these things. What back in the mid '80s, they used to talk about lights out factories.
Yeah.
Right. You'd go in, set it up, and you walk away from the factory, turn the lights out, and if the little yellow light came on, maybe it was time to go change a mechanism of some sort. Right. Right. We're headed in that direction. Sure. On these reflow ovens, on the whole process line. I think that's what this whole factory system's about.
Right.
You get the data, you learn how to what's important in that data, and then you take that and feed it back to the oven so it changes itself, or to the pick and place machine, or to the screen printer. But you realize that we have reflow guys absolutely know that most of the problems in an SMT line, they happen up at the screen printer, right?
Going back to your analogy with the Model T, you do realise in Europe we're still driving a lot of stick shifts.
Yeah, you have to choose. You have to choose your transmission, what gear you're in. Yeah. My truck, I don't. My truck's got a button on it that says automatic 4-wheel drive.
Max, what's your view on this?
Yeah, we're totally into the smart factory, into everything, to getting the oven to run itself. But actually, you should stay tuned for this year's fall. So we're introducing a new next reflow platform with the better consumptions, better and stuff like that too, with the monitoring, with smart factory. So you should stay tuned for that.
So new technology coming out from SMT Wertheim in the fall. What, Productronica time or SMT AI?
Somewhere around Productronica time, probably.
Productronica. Okay.
But we do have our 30 years anniversary as well, so there may be an event for that.
Yeah,
true.
That's true. That's a significant milestone. I think you've got a 60 or something. I mean, that was obviously a question I didn't include, but I mean, I'm assuming Productronica coming the end of the year, you guys usually gear up for new product releases. Have you got new things coming out at these shows?
We've got 2 or 3 things that we're looking at for that. I don't know which one's going to be absolutely ready for it.
Right.
We've got some very, very aggressive programs going on within BTU at this point.
Good. I always like to see new
They're excited. They're exciting.
Rehm is always coming out with new stuff. I mean, you must have some things coming down the pipe.
We will have a lot of new stuff. We will have a lot of interest tools also to help our partners, our customers, and that will came up during the Productronica. So you must wait a little bit. And then I can also explain more. But those will brilliant tools also to help our customers.
Excellent. Well, gentlemen, I wish you luck with your new projects coming down the road. And I also want to thank you very much for joining us today. It's been a fun debate, day of the show. So that's it for our Making Ovens Smart. I think we've got a good chance because we've got some very smart people here. Thank you for joining us today.
Thank you. Thank you. Thank you.
She was